Let's look at how we can use force diagrams to help us answer questions where two particles are connected. So let's say that we've got a car towing a caravan and they'll be connected by a tow bar. Okay, so we'll say the car has a driving force of, let's say, 10,000 newtons. We'll say that the car is 2.5 tons. We'll convert that into kilograms just so we're always working with the same unit. And then we'll have the caravan weighing 1,500 tons. Okay, so we've got the driving force, the masses of the two objects, and we're going to put a resistance on each of these. So let's say that the caravan has a resistance force of, let's say, 700 newtons, and the car has a resistance force of 1,300 newtons. Okay, so the question here would probably be find the acceleration of the car and the caravan. Remember, they're connected by a tow bar. We'll assume this is light and inextensible, which means it has no mass, which needs to be accelerated, and it's inextensible, meaning it doesn't stretch. So find the acceleration of the car and the caravan and find the tension in the tow bar. So let's look at how we could find the acceleration of these first of all. Well, let's notice the fact that this is an inextensible tow bar. So we could consider this as just one big single system, which has a mass of 4,000, a driving force of, I think we said 10,000, sorry about that, 10,000 newtons, and a total resistive force of 2,000 newtons. Now we can use F equals ma. Our resultant force is 10,000 minus 2,000. Our mass is 4,000. And we want to know our acceleration. So the acceleration is 8,000 divided by 4,000, which is 2 meters per second squared. Okay, so one of the tricks we can use is to just consider the whole thing as one system if the system is moving in the same direction. How would we find the tension in the tow bar? Well, we can take our acceleration. Imagine that we've added this to our sketch. We'll just give ourselves a little bit more room. Remember, double arrow, so we know that that is the acceleration. Okay. So, now let's consider just one of the particles. Usually, it's easiest to consider the caravan as it has no engine. There are fewer forces to consider. So we've got a caravan of mass 1,500. The only force accelerating this is the tension in the tow bar, and it has a 700 Newton resistance force. So, F equals ma again. T minus 700, so tension minus 700 must equal 1,500 times 2. That tells us that T is 3,700 newtons. Notice we would get the same figure if we drew a force diagram for this car. It would have tension and the resistance force of 1,300 newtons going this way. 2.5 ton and 10,000. Same calculation. 10,000 minus T plus 1,300 is equal to mass times acceleration. And that's going to give us 8,700 minus T. Rearranging this, T equals 3,700 newtons. So you see, it doesn't actually matter which one of the vehicles we consider. We'll get the same answer, however there are just fewer forces on the caravan, so it's much easier to use the caravan. One further example, which has a slight twist in its tail, is connected particles which are connected by a pulley. So just like everything else, we'll assume that the only forces involved are the weights. So that means we've got a smooth pulley up here, light and extensible string, as before. We've got masses of 3 kilograms and 5 kilograms attached here. So let's just colour code that so that when we work through, we can see what we're doing more easily. The main thing to consider here is just to look at it and think, well, which way would this system accelerate? I think that just an intuitive understanding will tell you that if you attach a 5 kilogram mass here, 3 kilograms there, the heavier side will move down, the lighter side will move up. So we'll use that in our workings. Let's do F equals ma for this first one. So let's draw ourselves a force diagram. The mass times gravity gives us the weight, 5g. And the only thing resisting that motion is the tension in the string. Similar for this 3 kilogram mass, 3g going down, and then we're going to have tension going up. So, as we know that this heavier mass will be moving downwards, we know that 5g minus tension will equal mass times acceleration. Okay, we know it's moving this way, so this must be the greater force. In this case, we're going to treat acceleration as a scalar because one will be accelerating that way, the other will be accelerating this way. Therefore, we're going to use acceleration as a scalar. We're just worried about the size of it. We can't say which direction it's moving in because they're both moving in different directions. Okay, we'll look at this one. In this case, we know it's accelerating upwards, so tension must be greater, minus 3g, and that's going to equal 3 lots of A. Again, it doesn't matter that acceleration's in a different direction, we're treating it as a scalar for now. Okay, so we've got two unknowns, T and A. Remember, G is just gravity, 9.8. We know that. So we can eliminate T by just adding the two equations together. So if we do blue plus green, add those two together, we will get 2g on the left hand side and 8a on the right, meaning that a is equal to a quarter of g, which is 2.45 meters per second squared. Okay, let's put that in as 9.8. Okay, so we've worked out our acceleration. Now if we want the tension, we can simply substitute our value of A back into either one of these. Let's do it in here. So we're going to get 5g, which is 49, minus t is equal to 5 times our acceleration, which will be 12.25. Bringing t over there and subtracting 12.25 from the 49 gives us t is equal to 36.75 newtons. Okay, so using simultaneous equations with our force diagrams and noticing that the acceleration is in different directions in this case. That's how we work with connected particles.